Kristen Atchison here, and we're going to do a hand calculation for a one-way ANOVA, and we're also going to do a hand calculation for a effect size. Okay, so here's our practice problem. A psychologist is interested in the effect of temperature of a room on a memory test. Does temperature of the testing room affect the memory test performance? Perform hypothesis testing, and here we've specified at 0.01. So we're not going to use 0.05 because we have a specification for 0.01. The other thing to note is that these are our small n's for each one of these groups, okay? So let's do our null hypothesis. Remember, it's best to try and practice this first and look at the calculations later. So please do that. The memory results for the three temperature conditions will be the same. That's our null hypothesis. And here's our mathematical representation. mu1 is equal to mu2 is equal to mu3. Our research hypothesis, the results for the three temperature conditions will be different. And our mathematical representation is not the null. Remember, that's because there's so many different ways that we can have a difference between these three groups. Our mathematical representation is just not the null. Remember, this is an omnibus test, that there's a difference somewhere in this data. We just don't know where that is yet. Okay, so for our F distribution, let's go ahead and calculate our degrees of freedom between. Remember, K is the number of groups. We have three groups. So 3 minus 1 is equal to 2. For our degrees of freedom within, we're just going to add the degrees of freedom for each one of the groups. Again, we have 5 members in each group. Minus 1, that gives us a degrees of freedom 4 for each of the 4 groups, or each of the 3 groups, I'm sorry, which is what goes in here, and we get a degrees of freedom 12. The same thing for degrees of freedom total. We're just going to add the 2 goes here, and the 12 goes here, and that gives us degrees of freedom 14. Okay, our cutoff value, again, we're using 0.01, so we're using a more stringent cutoff, and using degrees of freedom 2, 12, we're going to get a cutoff value of 6.93. Okay, so to the math. Okay, so first let's estimate the variance within each sample. Again, the first thing that we're going to do that is calculate our sums of square. Remember, this is why we've been practicing sums of square and talking about it so much, is because we use it in every single inferential statistic test we do. So the first thing we're going to do is add all these values together. 0 plus 1 plus 3 plus 1 plus 0 divided by the number 5 is equal to a mean of 1. And then we're going to subtract the mean from each group. So 0 minus 1 is negative 1. 1 minus 1 is 0, getting ahead of myself. And we have 2 and 0 and negative 1. We're going to square each value. I think I just probably could click those and they'd come up. There we go. We're going to square each value then. And we have 1, 0, 4, 0, and 1. And this is the sum of squares. So we're going to add all those values together and we get 6. That's our sums of squares for group 1, the 50 degrees group. For group 2, we're going to do the same thing. We calculate our mean for the scores, and we get a mean of 4. We'll subtract that from each group, from each value. Square each of those values. And add them together. Our sums of squared for group 2 is 6. And we'll do the same thing for group 3. We'll add those values together, average them, and we get an average of 1. We'll subtract that value from each. So we have 0, we have 1, we have 1, we have negative 1, and negative 1. Square those values. 0, 1, 1, 1, and 1. That makes that math easy for our sums of square of 4. Even my 8-year-old could do that one. Okay, so Now we've got our sums of squared for each group. Let's go ahead and get our values for G, which is the sum of our T's. And while we're here, we're going to go ahead and calculate our x squared, the sum of x squared too, that we can use in our sums of squared total. Remember how the sums of squared relate to each other, okay? Sums of squared total is equal to both sums of squared within plus sums of squared between. So you only need to calculate 2 out of the 3, and then you can solve for the third algebraically. We're going to go ahead and calculate all 3 just so that you see how they're all calculated. Okay, so our T is the sum, the total for each group. So you've already actually calculated that when you calculated your mean. So you could have recorded that earlier, but we'll just add up each of these values and calculate our total. And then G is the sum of our T's. So 5 plus 20 plus 5 is equal to 30. We have a G of 30. We're going to do the same thing for our x squared. We'll square each of those values. So all we're doing here is squaring each value. So 0 times 0 is 0. 1 times 1 is 1. 3 squared is 9. 1, 0. We add those together and we'll have 11. We'll do the same thing here. Square each value. Add them together. Same thing here. And we're going to do the sum of the x's, the sum of the x squares. Since we've already added up each column, we can just add those values together. So 11 plus 86 plus 9. We add those together and we get 106. Okay, and these are just components of those sums of squared between, sums of squared total, and sums of squared within treatments we're going to need as we move on. Okay, so first let's calculate sums of squared total. We just did our sigma is equal to x squared. We got that was equal to 106. We said our G was equal to 30. And we know that our N is equal to 15 because we have 5 people in each of the 3 groups. So then we just put it all together. 106 minus 30 squared divided by 15, which is equal to 106 minus 900 divided by 15, which is equal to 106 minus 60, which is equal to 46. So we have a sums of squared total of 46, okay? Now, notice this G squared minus N. We're going to use this again in our sums of squared between treatments equation. So this value here, this 30 squared, this 900 divided by 15, and this final value of 60, we're going to want to pay attention to this. Save this number. You've already calculated it. Why calculate it again? So we're going to use that value when we go into our sums of squared between treatments. Okay, sums of squared within treatments. This is the easiest one. You just add up the sums of squared for each treatment. We said sums of squared 1 was equal to 6, sums of squared 2 was equal to 6, and sums of squared 3 is equal to 4. Or add all of those values together. So 6 plus 4 is equal to 16. So our sums of squared within treatments is 16. Okay, and let's finish up with our third one, our sums of squared between treatments. Okay, we already have our T values. So we have T1 is equal to 5, T2 is equal to 20, and T3 is equal to 5. Okay, so we're just going to fill out the rest of the equation. We know that each little n is equal to 5 as well. So 5 squared divided by 5 plus, because we're sigma, right? We're adding it all together. 20 squared divided by 5 plus 5 squared divided by 5 minus, we've already done this piece, but if you cared to do it again, it would be 30 squared divided by 15. We already know that that's 60, so I'm just going to move on to 60 in the next bit. So here we have 25 divided by 5 plus 400 And then this we already know is equal to 60 from our previous calculations. When we do this, we get 5 plus 80 plus 5 minus 60, which is equal to 90 minus 60, which is equal to 30. So we have a sums of squared between treatments of 30. Okay, so we've done all our sums of squared now. Time to move on. Our degrees of freedom total, we had, remember, a total of 15 people. Minus 1 is equal to 14. We had a total of 15 people for degrees of freedom within treatments, minus the number of groups. We had 3 groups, so we have 12. And we had 3 groups is K, minus 1 is equal to 2. So there's our degrees of freedom. Now the formula that's tattooed on my forehead, sums of squared divided by degrees of freedom. We know that sums of squared between was 30. We know that degrees of freedom between was 2, so we have a value of 15 there. Sums of squared within, we calculated at 16. Sums of squared degrees of freedom within, we calculated at 12. That gives us a value of 1.33. Okay? So now our F. We will take our mean squared between that we just calculated of 15. We'll divide that by our mean squared within that we just calculated of 1.33, and that gives us an F of 11.28. Okay? So, to look up that cutoff score that we talked about earlier, you're going to use the degrees of freedom numerator. So that's whatever went into that previous, let's go back. Maybe I can go back. Oh, I'm ahead of myself. Okay, whatever one that went into that previous calculation where we had degrees, mean squared between on top and degrees of freedom and mean squared within on the bottom, so the numerator, denominator. So we use those two values to look up this 6.39. So again, that was 2 and 12. We comparing that to our calculated F of 11.28. So it's in the cutoff area, so we're able to, yay, reject the null. Remember, our F distribution looks a little bit different. So our cutoff value here is 6.93, and anything over here we cut off. Our 11.28 is in that area, so we're able to reject the null and support the research hypothesis. So how we'd write that in APA style is the temperature of the room made a difference in memory performance. Again, we have our degrees of freedom between, our degrees of freedom within, our calculated F. The value that we rejected it at, remember we're using a more stringent 0.01, and our eta squared. Wait, we haven't calculated that. I cheated and I went ahead and put it in here. We're going to do that next. So let me go through that, and now it goes to the what I wanted earlier. We will do, I'm sorry, I did eta squared here and we just missed it. Okay, so here is the eta squared. Let's calculate that. We know the sums of squared between treatments that we calculated was equal to 30, and our sums of squared total that we calculated was equal to 46. Now, if you hadn't previously calculated the sums of squared total, it's an easy fix. You just add the sums of squared within and the sums of squared between together, and you get sums of squared total. When you do this math, we get the 0.65. Okay, so that is where that came out in our decision here. That 0.65 came from that calculation.